Hi, it's Glenn. I'm here to show you the calculations for experiment number 1 in this empirical formula of copper oxide late night lab. So, let's see, the mass of copper powder used, I used 25.222 grams. You used some other number of grams. We did that, you just type in the number of grams that you used, not the number of grams that I used. The number of moles of copper powder, given that the molecular weight of copper is this many grams per mole. So there are many different ways to do this type of calculation. You may use whatever way you like. You may also use the way that Dr. DePrail may have shown you in the lecture portion of the course. My way is a little different, but there's absolutely no reason to stick with my way if you already have a preferred way. But anyways, number of moles. They're asking for number of moles. When they ask for number of moles, I start with number of moles, 1 mole. There are this many grams in 1 mole of copper. So 1 mole, 63.55 grams. This is copper, and this is copper. Now, I want to get an answer in moles, not an answer in moles per gram. So I need to put something here that is in grams. Why? That's so that I will be able to cancel out the G. I think probably in Dr. DePrail's class, you also cancel out units in this fashion, I think. Let me know if that is not the case. And I can show you more details about this method of calculation. Now, what in this problem uses grams, besides what I've just written down, 63.55? Well, we're talking about the copper powder. So the mass of the copper powder, that was in grams, and I can write that down, 25.222 grams of copper. So grams will cancel with grams, and I will end up with moles. So if I multiply 1 times 25.22 and divide by 63.55, I should get a number of moles, because moles is the only thing that's not crossed out, of copper. I will do that now with the calculator. I have done it already, and it is 0.3969. 0.3969 moles of copper. Now, how do I know that it is not 0.396884343? I know that because these digits here are 4. There are 4 digits. These digits here are 5. There are 5 digits. When you multiply and divide, the rule for significant figures is that you must use the lowest number of significant figures in the data. So the data are 63.55 and 25.222. This has 4. 4 is lower than 5, so the answer also must have only 4 significant figures. Here on the calculator, 0.3968, that's all I want. However, the last digit that I want, which is an 8, comes before another 8, which is more than 5. So I have to increase this 8 to 9. This is how to round off numbers in chemistry. Now, there's one other thing I had to say. There is only one figure in this 1 mole copper, but this 1 is not a piece of data. This 1 is a definition. It is a definition of this measurement, 63.55 grams per mole. So this number is not counted when I count significant figures. You can also consider this as a number that has infinite number of significant figures. So that's how to calculate the moles of copper. Let me go on down now here to the next portion of calculations. The initial mass of copper powder and the crucible. That's the empty crucible plus the mass of the copper that I added in. So that's going to be 113.222 grams. I just added that. I just added 88 plus 25.222, but you also measured that in the lab, or I also measured that in the lab, it's just I didn't write it down. So that one goes for this blank. The final mass of copper oxide and the crucible, that's the total mass of copper oxide and crucible, that's 119.572. So that goes in in this blank. The gain in mass equal to the mass of oxygen. Now that's going to be this number, 119.572, minus this number, 113.222. That number minus this number will be the mass that the crucible gained during my heating process. So here we are with 119.572 minus 113.222. That's 6.35 grams. So I have the gain in mass right there for part C. I have 6.35 grams. Now this is important here. When you do 119.572 minus 113.222, of course your numbers will be different from mine, but when you do this type of calculation, you have to take into account the significant figures rules for addition and subtraction. You add this up, there's a 0 here. Why? Because in addition and subtraction, the answer has to have the same rightmost place as the roughest piece of data. Now, both of these data go to the thousandths place, right there. That means both of these data have the same level of precision, or the same roughness. So that means the answer has to have the same level of precision. The answer has to go to the thousandths place also. So the correct answer here would be 6.350. It would not be 6.35. In chemistry, 6.35 means a different thing than 6.350. 6.35 would mean that you're not sure if it's 6.345 or 6.346 or 6.351 or 6.354. It could be any of those, anything in between. However, 6.350 means that you are sure it is 6.35, and then it may be 6.3504, it may be 6.3503, it may be 6.3502. It's that sort of thing. All right, now part D, the number of moles of oxygen in copper oxide given an atomic weight. Okay, so now we do the same calculation as before, but we do this for the oxygen. So this is the mass of oxygen. And try to picture this. Let me go back to late night lab for you. Late night lab. Okay, so here, the crucible with copper in it was on the Bunsen burner. It was brown or orange. And when you turned on the Bunsen burner, you started to heat that up, and then it became black, right? So why did it become black? There was a chemical reaction. And the chemical reaction was with the air in this virtual lab. So oxygen came in here. So this thing is heavier than it used to be. I didn't put anything in here, yet it is heavier by about 6 grams than it used to be. Something must have come in here. What is it? It was air. Air molecules came in, and you can't, usually you don't weigh air molecules, but in this case there was a chemical reaction, and so a whole lot of air molecules got used up and incorporated in with this solid. So we have 6 more grams in here, all due to presumably oxygen from the air. So back to here. So what does this mean? This means this is from oxygen in the air. That is in that black solid stuff at the bottom of the crucible, and it comes from the air's oxygen. So now let me do the calculation. They want the moles of oxygen. Is that what they want? The gain in mass, number of moles. Yes, the moles of oxygen. So I start with moles. 1 mole of oxygen weighs 16.00 grams, and I have 6.350 grams of oxygen. And so I take my calculator and I do a little bit of a 6.35 divided by 16, and that's 0.3969. Again, 0.3969. Now that's That's odd. That's 0.3969 moles of oxygen. So what does this mean? Okay, now, it's very good, very useful that we got the same number of moles of oxygen as we had moles of copper, 0.3969. Notice that on the calculator, the number that you actually got for oxygen, or that I actually got just now for oxygen, 0.396875, is a little different from the number that I had gotten for copper. But when you take into account the chemistry significant figures rules, they are exactly the same number, 0.3969. Okay, so I will continue now. Go down here, and I'm going to calculate the mole ratio. I'm going to do the moles of copper powder divided by the moles of oxygen in copper oxide. So what does that mean? That means the following. Can I scroll down on the notepad? Yes, I can. Okay, so moles of copper powder. How many moles did I have? Remember, I had 0.3969 moles of copper powder. All right, and divide that by moles of oxygen. You see over here I have 0.3969 moles of oxygen. Okay, so what does that mean? Well, when I do the division, of course, these cancel and I get 1. So the mole ratio is 1 mole of copper per mole of, I gotta move this away, of oxygen. So this mole ratio is 1. Technically, you shouldn't write 1. Technically, you should write 1.000. Why? Because here there are 4 significant figures. So technically, the answer should also have 4 significant figures. However, when you do the mole ratio, I'm not going to take off points the way I do with measured data. The mole ratio, it will be fine if you just left it as a whole number. But if you want to use all the significant figures, that's great too. Okay, now according to the molar ratio, what is the empirical formula of copper oxide? Now, there is a little web page from some online textbook, product or something, or maybe it's some other type of chemistry website, but there is a web resource in your lecture course material that shows how to calculate the empirical formula of something. I'm just going to do that for you here. Right, now, to calculate the empirical formula of something, let me just thin out this pencil. Okay, but this is not the pencil. So excuse me, I just need to get the pencil again. Here we are. Thank you. All right, to get the mole ratio, this is what you do. Oh, that's too thick, sorry. All right. Okay, so you write down each element of the compound that you think you're getting. In this light lab experiment number 1, we started with copper, and oxygen got incorporated in there during the heating process. So I see there are 2 elements involved, copper and oxygen. You can, we know that the mole ratio was moles of copper to moles of oxygen. So the moles of oxygen will be 1 here, and the moles of copper will be 1 here, because the mole ratio was 1. Here, let me help you think about that in a much simpler way. You write the copper that you used in late night lab, and you write the oxygen that came from the air in the late night lab. The meaning of this is if you write the number of moles that you got for copper and the number of moles that you got for oxygen, you just wrote the formula for the compound, the copper oxide. This is the formula, in much the same way as H2O is the formula for water. There are 2 H atoms and 1 O atom in every H2O molecule. So in every copper oxide unit, there are 0.3969 copper atoms and 0.3969 oxygen atoms. However, you can't have 0.3969 copper atoms or 0.3969 oxygen atoms. You can't have a fraction of an atom. If you were to split an atom like that, the whole world would blow up, or something catastrophic like that. You know, you would have a very high energy event on your hands if you split an atom into 0.3969 parts. Now, how do you solve this problem? How can I express the formula for copper oxide using whole numbers if all I have are this many moles of copper and this many moles of oxygen? Well, if I just divide by the lowest number here on the copper side and on the oxygen side, that will give me the mole ratio as I calculated in the previous, just a few minutes ago. So I have divided by the lowest number. Well, they're the same number, so it is its own lowest number. So this becomes 1, and this becomes 1, and the formula is copper 1, oxide 1. When the subscripts are 1 here, I mean when the mole ratios are 1, you can just write CuO. You don't have to write the 1. If you just write the chemical symbol of the elements, everyone knows that you mean one of them if you haven't written some other number down here, as done in H2O. There's 2 H's and 1 oxygen. Okay, that is known as the empirical formula. It is the chemical formula for something that you figured out by doing experiments. That's the empirical formula. Now, what if in my lab, instead of finding 0.3969, what if I had found 444 moles of copper and 0.8888 moles of oxygen? Then I would divide by the lowest to get the mole ratio, and that would get me Cu1O2, which would be CuO2. This compound does not exist in nature, but just to show you a little more on the empirical formula calculation, I show you this example. So, according to this molar ratio, the empirical formula for my copper oxide was CuO. Now, what about the balanced equation? Okay, let me show you about that balanced equation. You started with copper, and the late night lab revealed to you that oxygen came in from the air. That's why the mass increased. So when you mix copper and oxygen, what do you get? Well, you get this black stuff, and we know the formula is CuO because we just figured it out. I mean, I just figured it out. So I need to balance this equation now. If I put a 2 here, and I put a 2 here, then the equation will be balanced. So that's it. That's how to solve the problems for experiment number 1. I'll make a separate video for you for experiment number 2. Thank you.